Hello there. Welcome to another problem session. This is coming from, once again, from 2020 JEE Advanced Physics Paper 1. Okay, so many of these tests, if you do last 10 years exam papers, probably it could good enough preparation in addition to your regular physics classes. Okay, so here are actually there's a lot of formulas here and concepts from modern physics part of the intro physics. So this question about black body radiation. So you're thinking of light bulb as some kind of black body with surface area this much, and the surface temperature of the filament, as a surface temperature is 2500 Kelvin. And these are reasonable numbers, okay? And you're looking at it from far away distance. So details are not important about the filament. And pupil size is 3 millimeter radius. That's also pretty reasonable. And constants are given. And there are these 4 questions here, A, B, C, D, okay? And each one have to test it as correct or false, because any one of them be correct. So each has to be tested. So let me get a little space here to calculate for the A. So I can just move this down here and get myself this space. Okay. So how much power is radiated by the film? There is it's already given a hint, Stefan-Boltzmann constant given. So there is a law like flux radiated out, okay? So this is the total, and this will be watts per meter square in the units, okay? So like a power 1 meter square is equal to sigma T to the power 4 law. You probably know this, and this is sigma. So if the filament, from the entire thing that comes out of the filament in all directions, the entire thing, that will be this. So temperature is given Kelvin, that's the Kelvin, and sigma, we just have to multiply it. So this is 5.67 times 10 to the minus 8 Kelvin to the power 4, and I have to multiply by 2.5 times 10 to the power 3 Kelvin to the power 4. So don't see that all of this 4 power k will cancel out. This will cancel out, and so what you will be left with the watt over meter square. Okay, so I'm going to do this calculation and we'll be back. All right. Okay, so I did the calculation here and I got this as a flux. But the question is about its power, which means I got to multiply by the area part. So we want power will be flux radiated times area of the filament. That's the surface area of all this filament, So if you just kind of model it as some kind of material with a surface, so all the surface area added up, and that's 64 millimeters square. So I get 2.22 times 10 to the power 6 watt over meter square, and this millimeter square. So I have to make it 10 to the power minus 3 meter, each millimeter will be that much square. So this powers will get rid of this power with that. So that's the watt. So I just need to do another calculator quick. Okay, so the calculator gives me 142 watts, and it says it's supposed to be between this and this if this answer is correct. So A is not correct. Okay, so we can use these values maybe later. So I'm going to write these values and make room for B. Okay. Okay, so how much of this radiation entering the eye? Well, so this radiating out at you can say, this many watts per meter, this many watts, so that's much totally coming out, and the eye is little opening about radius r equals to 100 meter away, and this one the radius is a little r, which is 3 millimeter. So if you think about this as area, that's the area that's was going to come through here, and this energy is spread out over this whole sphere. So you can say this energy is going to power radiated is spread out over 4 pi r square, and only pi r square, this is circle, only pi r square of that is into I. So this will be power into I, should be like that, into 1I. 2I will be 2 pi r square. So if you look at this, I've got 142 watts, and you could say pi cancels out over 4, and r over r is square. This is in millimeter, and this one is in meter. It's 100 meter. So this will be 3 times 10 to minus 3, make it meter, and this will be 100 meter. So meter got cancelled out. So this will be in the watts. So this is 142 times 9 over 4 times 10 to the power minus 5, but then minus 10, squared it minus 10, this many watts. This looks like it's going to be in the range, and it actually is 3.18. You calculate this out, that's related minus 8 watts. So almost like 31.8 nanowatts, and it is in this range. So the B is correct. This is incorrect. So this is basically power. This is the intensity. This is spreading everywhere. This net power is going everywhere, and only a small part of that power, if you look at in this solid angle, that is it, that went in the solid angle is the one that went in the eye. This is the eye here. Okay, so that's a pretty good problem. Actually, it tests your thinking about how geometrically things can happen. All right, so I'm going to erase this a little bit and then try to address C and D. Okay, so to answer C, it's another law, okay? It's called Wien Displacement Law, and it uses Wien displacement constant. And it turns out, you can see right here, there's a hint, meter times Kelvin. So it turns out that lambda at a maximum intensity, so intensity kind of with a lambda kind of drops up in both ends, and there is a particular lambda at which is maximum. Intensity maximum. So this lambda max. And this times temperature is actually a constant, and that's the Wien displacement constant. For black body. And the question is about that lambda for this temperature is going to be this nanometers. So let's just figure this out if it's really true. B is already given. Interesting that they give you this, but you're supposed to kind of memorize this. And temperature is 2.5 10 to the power 3, right? Or 2500. Okay. And this is meter, and K, and I want to make nanometer, then that will be 10 to the power 9. So it's looks like 1.160 will come out. So all these powers of 10, that's so 10 to the power minus 6, 10 by 9 makes it 10 to the power 3. And we just have to figure that on my calculator. And I'm going to do calculate and come back. So I found it 1.16 times 10 to the power 3 nanometers, and which is correct. So C is correct. Okay, so now we have reached down to the last one, and let me erase and come back to you. Okay, so we're supposed to now say, all right, we got all kinds of wavelength, and the maximum was maximum happened at that, but you can say that just want to count the number of photons that's entering my eye. That's this problem, and instead of taking that, just take some average wavelength is this. I don't know how they average this, but this is what's given in the problem. So if all the photons entered had this wavelength, that's what we can assume. And the total number of photons entering per second into the eye, so this is the power. So basically what we have is one photon has energy E of 1 photon, and n times E that enters the one eye per second, then this should be equal to the P in one eye. That's what we have. So we're supposed to say that if you calculate n, will it come in this range, P1I with this lambda. So what is E lambda? So we already know this. If we know this, then divide that out, fine. It's going to be HC over lambda. And I think H, Planck's constant is given, and C is given. So H is 6.63 10 34 joules second, and C is 3 times 10 to the power 8 meter per second. The second will cancel out. And lambda is 1740 times 10 to the power minus 9. So when this will be meter, so this meter will cancel this meter, and once we work this out, we'll have how much energy in watts. So this numerator is already, we know, 3.18 times 10 to the power minus 8 watts. So this will be this number will be in the joules. Let me work this out and come back and complete these numbers. Okay, so I completed these calculations over here. So I got this much energy per photon of this wavelength. So I had to remember this formula. If you don't remember this formula, probably you can say E equals to H times frequency, and frequency will be C over lambda. And then I plugged in here, and this is between these two values. So this is correct too. So the answer for these questions will be B and C and D. These are correct, and A is not correct. Okay. If you like this video, please hit a like button. Appreciate that. Thank you, and I'll see you in another video. Okay, bye.